So again, kind of reviewing, estimating our population proportion. This is what we were talking about last class. So you can't actually figure out your true proportion because you don't always know the full population that you're dealing with. So you have to take all these different samples and kind of estimate what your proportion is going to be off of those. So my example I have here is how much can you say really from just taking one sample? So our example, I have a huge mystery bag of beads and I take a random sample of 50 beads from it. I do not know the true proportion of red beads in the bag, but in my sample 18 of them are red. So the one thing we know for sure is 18 out of my 50 are red, which what is that as a percent? 36%. So we know from my sample, 36% of my sample are red beads. So then knowing that, what could we potentially claim about the full population of beads in my giant mystery bag? We could say that 36% of the beads in the bag are red. Yeah. But can we be very confident in that claim that out of the entire bag, 36% of them are red?
Yeah.
You're going to be confident in that?
No.
No. You're not going to be very confident, not very confident, because we only took one sample. So really, if you just have one sample out of something, it's not going to make you very confident in whether or not that is a true reflection of the full population. So what I did is I then repeated this 99 more times, and I created this dot plot down here, which this dot plot should look familiar. We were dealing with some of these last time. So this is actually referred to as a sampling distribution. So where each dot on here is one sample. And so of that sample, we did like what we did above, and we figured out what proportion of that sample was a red bead. So it's 1 p hat. Remember, when we take a proportion of a sample, we call that a p hat. So our number of samples, we took 100 of them. We took the 99 that I did plus the one that we talked about up above, so we have 100 samples. Our sample size is 50 though, because we pulled 50 beads each and every time we took a sample. So now looking at our sampling distribution that we have here, what would we claim is a true proportion of the red beads? Doesn't it kind of look like maybe my majority is kind of in between here? So what would be in between 0.18 and 0.24? 0.20. So I would say that my true proportion, P, is approximately 0.20. So when estimating true proportions, we like to estimate an interval for which the true proportion can exist in. Because, yeah, we can say it's approximately 0.20, but the chances of it actually hitting that one value is not very likely. So what we like to do is we like to try to create an interval and say that within that interval is going to be our true proportion. So when we do that, the interval we use is about 2 standard deviations from the mean. So if you think back to the first part of statistics we talked about, there's our mean right there in the middle, 0. There's 1 up, 2 up, 1 down, 2 down. Does anybody remember what percent is in between 2 below and 2 above? Mm-hmm. 95% of our data is in between 2 standard deviations below and 2 standard deviations above. So to get the interval, we go 2 standard deviations below, 2 above, and that gives us a 95% chance of getting the actual proportion within there. So, keeping that in mind, we want to try to figure out where 95% of our data is going to fall within this graph here. So if I'm looking at this, I think 95% is kind of from like here to here. Wouldn't you agree about 95% of our dots are in between those?
Yes.
Yeah, we're looking for the majority here. So this is approximately 0.14 up to 0.26. So now with my interval, I can be a lot more confident in my claim. So how confident are you that your interval claim? Pretty confident. Because I could take samples that are a little more on my higher end. I could get samples that are a little more on my lower end. But it's definitely going to be somewhere in there. So then represent in this form plus or minus format. What we do is we take what we originally thought our true proportion was going to be, our 0.20. What did I subtract from 20 to get me down to 14? This minus what got me down to here? And then from this plus 0.06, does that get me to my 0.26? So it's 0.20 plus or minus 0.06 is how we get our interval there. So by subtracting the 0.06, we get to our 0.14. Adding it gets us up to our 0.26. So in this case, that 0.06 is what we call our margin of error. Now, it's not saying that we actually made a mistake. It's just saying that based on which samples we choose, it could end up being anywhere within that range. Questions on that so far? As he was saying, you're not making this definitive statement of this is what the true proportion is. You're never really going to be able to find out what the true proportion is. You're kind of making your estimation based off of our p-hats, and that's what we were doing on our sampling distribution. We found generally where we thought the average was going to be, and we were making our statement off of that. So when you're making your confidence interval, you can state that you are 95% confident that between here and here is where our true proportion is going to be. You cannot say that there is a 95% chance that it's in there, because that's not what you're saying. You're not saying what is the probability that it's in there. You're stating that with 95% confidence, your true proportion is going to be somewhere in that range. And as he was saying, by going out 2 standard deviations, the chances that it's actually in there is very high. You all right, Paul? Okay. So remember that plus or minus 2 standard deviation covers 95% of your data, which I went over on my little picture up on the first page. AP Stats guy just went over it also. So I am 95% confident that the portion of red beads is between. You want to take your p-value and subtract your margin of error, which your margin of error is 2 standard deviations. And you want to take your p-value and add your margin of error to it, which again is 2 standard deviations. So you're subtracting and you're adding your margin of error to it. Now there used to be this big huge formula that you would have to do to actually calculate your margin of error, but we don't have to do that anymore. All you have to remember, your margin of error is 2 standard deviations. So with these problems, what's going to happen is they're going to give you your standard deviation. So all you have to do is multiply it times 2 to figure out what your margin of error is going to be. And then a little note here. In order to decrease your margin of error, you must increase your sample size. So like with our 50 beads we were talking about, if I wanted to decrease my margin of error for that, I should have taken samples of 100 beads, or 200 beads, or 150 beads, whatever. Increasing your sample size is what decreases your margin of error, because it makes your data more accurate. So let's go back to our cell phone question we dealt with in our warm-up today. So we had here the true population proportion of juniors who had cell phones. Our p-value we got to be 0.71. So we said 71% of our juniors had cell phones. Our p-hat for our freshmen was 0.58, based on the sample we had for our freshmen. 0.58, so 58% of them had cell phones or said they had cell phones. So again, the sample of proportion, or the proportion sample for your freshmen was less than our total population proportion for your juniors. So then the question becomes is, do freshmen really have less cell phones than juniors do? So we will assume that the freshman number is too low and that the true proportion is what the junior proportion showed of 71%. So we would like to determine that if we draw a sample from a population where the proportion of cell phone ownership is 71%, that getting a 58% could be a likely outcome. That's what we're trying to figure out. So I ran a simulation down here for you. So we got this beautiful sampling distribution that I ran for you guys. They want to know how many of the 100 simulations had a proportion less than or equal to 58. So let's look at our chart here. Here's my 58%, which would be this line here. So we want to know who had 58% or less. So count up our dots there. 9, because you forgot the or less. So 9 of them had 50% or less. So they want to know how likely is that a sample of 52 would result in a proportion of 58 or less. Is that going to be very likely? I got 100 samples here, and out of those 100 samples, only 9 of them were 58% or less. So was it very likely? No.
No.
Not likely. Only 9 of the 100 samples were 0.58 or less. So the chances of having that, very slim to none. However, if we look at our next question, which falls on our next page, is it possible that a cell phone ownership rate of 71% could have a sample proportion of 0.58 or less? It's possible because it did actually happen on our sampling distribution. You did have a few dots there. So it is possible. Some of our samples did show that. So it's possible, but as we just said, it's not very likely that it's going to happen, but it could. So D, what they want us to do is they want us to estimate a margin of error based on our little chart that we had there. So let's go back to our sampling distribution. We're going to estimate our margin of error. So remember, our margin of error should be 2 standard deviations above and below, which means we're looking for 95% of our data. So I'm going to say approximately 95% of my data would fall maybe about here to here. Does that look like it's about 95%? Yeah. Again, we're estimating, so you might be off a little bit, and that's okay. It's an estimation. So if this right here, here's my 0.71. This one is at 0.81, so how much did I add to get up there? 0.10. This one is approximately at 0.61, so I subtracted my 0.10 to get down there. So that our margin of error was how much? 0.10. So our margin of error was 0.10 based on our approximation on our graph there. So then they want us to now estimate a 95% confidence interval for that. So I'm going to do 0.71 plus or minus my margin of error, which was 0.10. So 0.71 minus 0.10 gives us 0.61. And then 0.71 plus 0.10 gives us 0.81. So our 95% confidence interval for this would be from 0.61, so 61%, up to 81%. So we're saying that either 61% or up to 81% of the students have cell phones. That's our confidence interval. We can say with 95% confidence that that proportion of students have cell phones. So now what they're telling us is they actually went through, they ran the calculations, and our standard deviation is 0.065. So knowing that, they want us to now calculate what our actual margin of error is. So our actual margin of error would be 2 times whatever your standard deviation is. So 2 times our 0.065. Which that gives us what? .13. Were we close with our estimation that we made? Yeah. I mean, we had 0.10. It actually turned out to be 0.13. We were pretty close. So that's good. So now, knowing what our actual margin of error is, they want us to calculate our 95% confidence interval. So our 71%, our 0.71, plus or minus our margin of error of 0.13. So 0.71 minus the 0.13. What do we get? 0.58. And then our 0.71 plus our 0.13, 0.84. So therefore then, our p-hat of 58%, does that fall within our confidence interval?
Yeah.
Yeah, it ended up falling within there. So that's saying that it is possible that our 58% was an accurate number that we could actually end up using. It's within our confidence interval. Since we don't know exactly what it is, we use our confidence interval to figure out our estimation. All right, let's try another one. So we have a beverage company who's trying to test a new brand of cola here. They will launch the product if at least 25% of their drinkers will purchase the product. So they devised a simulation based on the assumption / requirement that 25% of the cola drinkers will buy the product. So each dot here represents the proportion of people who preferred Stevens' new product. Each sample size is 50. So each dot represents a sample of 50 people who were surveyed. So this means 38% of those 50 said that they liked the drink. So remember, this one says 26% of that 50 said that they liked the drink. So the mean and standard deviation for the distribution are shown below. So there's our mean, there's our standard deviation. They always put those up in the little corners for you. So let's take a look at our questions over here. So assume the set of data is approximately normal and the company wants to be 95% confident of its results. Calculate the margin of error on the assumption that the proportion of the people who like the soda is 25% or 0.25. Do we actually need to know that to get our margin of error? No. What we need to know for our margin of error is our standard deviation, which if we look at our graph on the last page, what was our standard deviation? 0.062. So let's multiply that. 2 times 0.062. What do we get? Yeah. So our margin of error is 0.124. So 50 cola drinkers are randomly selected to take a blind taste test, and 9 out of the 50 participants preferred Stevens' new cola product to products A and B. So does the sample proportion obtained from the blind taste test of 9 out of 50 fall within the margin of error developed from the simulation that they ran? So let's first figure out, well, what is our percentage if we have 9 out of 50? So 9 out of 50 gives us 0.18. So 18% of them said that they liked it. So based off of what they want 25% at least in order to run it. But then with our margin of error of plus or minus 0.124, we have to figure out if 18% is going to fall within there. So 0.25 minus our 0.124, what do we get? There it is. And then we'll add at 0.25 plus our 0.124. 0.374. So does our 0.18 fall within our margin of error? It doesn't? Pretty sure it falls within that range. So yes, it does fall within the range of our simulation. So the company decides to continue developing the product even though only 9 out of 50 participants preferred its brand of cola in the taste test. Describe how the simulation data could be used to support this decision. Now remember, they said they wanted 25% of the people, to actually like it in order to continue going on further with making the product. So why are they still going to run if only 18% liked it? Some people still liked it, but they wanted 25%. It's not the entire population, which is why we created our confidence interval. And our 18%, as we just said, it fell within our confidence interval, didn't it? So they're good to go. That's true too. So because it is within the 95% confidence interval, there could be enough people out there. Oops, I spelled that wrong. Who like it. You've also got that whole thing because it's a confidence interval. We could be off a little bit. We didn't have the full population. We only looked at 50 people out of how many people that buy soda in the entire world. So our next example, we have in May of 2002, the Gallup poll asked 537 randomly sampled adults the question, generally speaking, do you believe the death penalty is applied fairly or unfairly in this country today? So of the people who answered, 53% answered that it was fairly applied. 40% said that it was unfairly applied. And then 7% said that they didn't know. So the sampling standard deviation is 0.02. What can we conclude from this survey and create a 95% confidence interval for the proportion of all U.S. adults who believe the death penalty is applied fairly? We're looking at the ones who feel it's applied fairly. So for this one, let's start with what percentage said that they felt it was fair. So our P is going to be 0.53, so it was 53% said that they felt that though it was fairly applied. Next thing we have to figure out is our margin of error. So that's 2 times our standard deviation of 0.02, which they gave us within the problem. So that gives us a margin of error of 0.04. So then for our confidence interval, it's going to be our 0.53 plus or minus our margin of error of 0.04. So let's subtract those. 0.53 minus 0.04. What do we get? 0.49 up to, so 0.53 plus 0.04 would be 0.57. So there's our 95% confidence interval. So we're saying from 49% to 57% believe that it's applied fairly. So what can we conclude then from the survey? We got to actually make sure we answer that question up there. Well, I got 49% to 57% think it's applied fairly. What can I conclude from that? Is that the majority? Is that not the majority?
That's in between. It's the majority at one extreme, and it would be less than half on the other extreme.
It would be less than half, yes. But this one was only 40%.
True, so that'd be lower, so yeah.
Yeah. So we could say with 95% confidence, that the majority of people think it's applied fairly. All right, we got one more example. So an insurance company checks police records on 582 accidents selected at random and notes that teenagers were at the wheel in 91 of them. The standard deviation is calculated to be 0.015. So create a 95% confidence interval for the percentage of all auto accidents that include teenage drivers. So the first thing we have to do is we have to get our P, which would be 91 teenage drivers out of all 582 accidents. We'll go to the nearest hundredth for this one. What does that end up giving us? 0.16. So then after we get our 0.16, what do we need next? Margin of error. I heard somebody whisper it. I don't know why you guys aren't chatty today. Yes. So 2 times 0.015 gives us a margin of error of 0.03. So then our P plus or minus our margin of error would give us 16% minus 3%, so 13%, up to 19%. So there's our 95% confidence interval. From 13% to 19% of accidents, teenagers were behind the wheel. That's not necessarily saying they caused it, but they were behind the wheel when the accident occurred. So B, a politician urging tighter restrictions on driver's licenses to teens says, in 1 of every 5 auto accidents, a teenager is behind the wheel. Does your confidence interval support or contradict this statement? And explain. So what should we figure out first? Well, not necessarily that, but what percentage is he giving people? What is 1 out of every 5 equal to as a percent? So this would be 0.20. Does that fall within our 95% confidence interval? No. So, does our confidence interval support or contradict this statement? It contradicts this statement, and then you got to give us a little explanation as to why. And it would be because 0.20 is higher than our confidence interval. So it contradicts the statement because 0.20 is above the highest value. Anything along those lines would be fine.